Okay, I'm going to spend the first couple minutes very quickly reviewing what we talked about last time, but I'm also going to address some of the questions I got last time briefly. So let's start with a quick review of what we talked about. So we basically discovered that there's this function called the Weierstrass-Phi function. It is a meromorphic function on a complex torus, and it only has one double pole at the origin. And so based on the theory we had discussed previously, that makes it sort of the simplest meromorphic function, if by simplest you mean has the fewest number of poles on the torus. And as a matter of fact, I told you that if you take the Weierstrass-Phi function and its derivative, those actually sort of generate the field of elliptic functions in the sense that every elliptic function is a rational function in phi and phi prime. And somebody asked me last time, I think it was a cocky, kind of to sketch the proof of that. So I wrote just a little bit of something today. I'll go through it really quickly. So basically, take an elliptic function f. If f is an elliptic function, then f of z plus f of negative z over 2 and f of z minus f of negative z over 2 phi prime z are also even elliptic functions. And not only that, and that's easy to see. And not only that, but f is the first guy plus phi prime times the second guy. And so really it suffices to show that the subfield of even elliptic functions is generated by phi, okay? Because all the rest of the elliptic functions are taken care of by this relationship here. So to show that the subfield of even elliptic functions is generated by phi, the strategy, I'm not going to go through it, but the strategy is to build a function that has the exact same zeros and poles as your given even elliptic function, using only functions that look like phi minus u, where u is some complex constant. And why is that enough? Well, suppose you've done this. Then if you take the ratio of your even elliptic function f with this new elliptic function, because the elliptic functions are a field, you know you get a new elliptic function. And because f and g had the same zeros and poles, you know that this ratio won't have any poles. But there's a proposition above up here that says any elliptic function with no pole is constant. So what this tells you is that your starting even elliptic function f is basically some constant times an elliptic function with the same zeros and poles as f, made out of nothing but these expressions phi minus u. And so it's a rational function in phi, and you're done. And just to give you an idea of what it takes to show this, you do need to use both the double periodicity and the evenness of f, I think 2 or 3 times in the proof each. You also need this fact that I should have said last time and I didn't. The Weierstrass-Phi function takes on every value in the Riemann sphere. The Riemann sphere is just the complex numbers, union infinity, twice, counting multiplicity. By multiplicity, I mean, if you look at the zeros of phi minus some complex constant, the multiplicity of the 0 is 2, okay? And as a matter of fact, we know exactly which values have multiplicity 2. I won't go into that, but when I send these notes out, you can read that. And then you also need the residue theorem at some point applied to meromorphic functions on the complex torus. So it's some work, but there's a little sketch of it. The other thing last time was I felt like I didn't stress enough why this proposition is true, because we're going to use it heavily. The proposition is that phi prime squared is a cubic in phi. Okay, and so why is this true? The reason I didn't really talk about it a lot last time is you do need an observation from the actual proof of this proposition, and I didn't want to write out the full proof. But let me give you just a quick sketch. Essentially, you know that phi prime has a triple pole at 0 and 3 simple zeros elsewhere, not at the origin. Okay, and using the proof of the above proposition, if you take, this is a typo, if you take phi prime squared as your even elliptic function, because you know phi prime is odd, so its square is even, then you can apply this above proposition. And this function here, up here that I referred to, the function that you build that has the same zeros and poles as your given elliptic function, you see from the proof that it ends up looking like this. So it'll end up looking like the product of phi of z minus phi of ai over the product of phi of z minus phi of bj. And what are these ai's and bj's? They're non-zero, first of all, and they're fine. And when you plug them into phi, you get finite values. You don't get infinity. Okay. But more crucially, if these ai happen to be non-zero half lattice points in your lattice, then they will only be included in this product half as many times as the multiplicity with which they occur as zeros of phi prime squared. Now, it turns out that, and we've already seen this, I think we talked about this last time, the zeros of phi prime are exactly the half lattice points, right? So they will only be included up here once, according to this construction from the proof of the last proposition, okay? Because they're simple zeros of phi prime, so they're double zeros of phi prime squared. Since they're multiplicity 2, we should only be including them half as many times as they occur, so once, okay? So we're gonna have 3 AIs, basically. Now, how many BJs? Well, here's the thing, what are the BJs? The BJs are the non-zero poles of our even elliptic function, phi prime squared. But there are no non-zero poles, because phi prime only has a triple pole at 0. So effectively, if you let your even elliptic function be phi prime squared, what you end up with is phi prime squared equals a constant times this function right here, but there is no denominator, and there are only 3 factors in the numerator. Well, that gives you exactly that phi prime squared is a cubic in phi. Okay, so that's what we were trying to show. Okay, so there's that. I think the only other question I got was a Cocky's question about elliptic curves having nice sheaf theoretic properties. I don't really want to get a whole lot into that, but what I did do is I sent you guys a link to the last lecture, and I put a brief actually correct explanation of why elliptic curves have nice sheaf theoretic properties that other genus curves don't have. So if you're interested in that, go check out the YouTube video, look at the video description. There's a little paragraph down there. Okay, what else did we do last time? Well, we saw the very important theorem that if you look at the following map, z goes to phi of z, phi prime of z1, where z is non-zero, and then if z is 0, send it to the point at infinity. This is a biholomorphism from the complex torus given by your lattice to the Weierstrass normal form of the elliptic curve given by this lattice. And so what that means is every complex projective elliptic curve is admitted by a lattice, and we will see later that the converse is true. So you can always make a complex torus biholomorphic to a complex elliptic curve, projectivized complex elliptic curve. And we went further than that. We also saw that because there's an addition of points on a lattice and hence on a torus, you can port that addition over to this elliptic curve. And what you end up seeing is that this map up here between the torus and the elliptic curve is not only a biholomorphism, it's actually a group isomorphism. So you get a very strong connection between complex tori and complex elliptic curves. And let me just remind you geometrically how the addition law works for elliptic curves. The strategy is take some elliptic curve. I'll draw a different one than I did last time. Okay, let's say you want to add 2 points on this thing, P1 and P2. Basically what you do is you draw the line through them, and then by Bézout's theorem, you know this line will hit the curve at a 3rd point, and we'll call that point negative P3. And then it turns out the sum of P1 and P2 is given by the additive inverse of negative P3. But we saw last time how to take additive inverses. You just reflect the point over the x-axis. So this point right here would be P1 plus P2, which maybe we'll call P3. Okay, so that's how it worked geometrically. And then I also gave you actual formulas for the coordinates of the sum of 2 points, depending on whether or not the 2 points you're adding are the same or different. Okay, and remember that if you're adding a point to itself, what is this orange line that you draw connecting the 2 points? It's the tangent line to the elliptic curve. Okay, and I think that's about where we stopped. So let me continue on now. What we're now interested in is we've got this group law on the elliptic curve. Whenever you have a group law, you should be interested in what are the points that have finite order. Okay, what are the points such that we add, what are the points P such that when we add P to itself, it only takes us finitely many additions to reach the additive identity, which remember is the point at infinity in this group law. The set of all points of finite order is called the torsion subgroup. And I'll let you check this is actually a group. There's nothing to check at all, really. Okay, but the points of finite order on the elliptic curve form a group under addition. Okay, so more precisely, if I give you a natural number n, what can we say about points of order n? And when I say order n, I don't really mean exact order n. I mean maybe order n or some order dividing n. Okay, so if I want to specify that a point has exact order n, then I will say that. I will say exact order n. On the elliptic curve, y squared equals f of x over k if we allow coordinates to maybe be in some field extension of k as needed. Okay. Well, if you're going to talk about points of finite order, what's the easiest place to start? The easiest place to start would be points of order 2. So points such that they themselves are the identity, or when you add them to themselves, you get the identity. Well, we've already answered this. We already know precisely what these points are. Of course, the point at infinity has order dividing 2 because it has order 1. And then we also know that EI comma 0 will be points of order 2 on our elliptic curve, because if you take any point on the x-axis and you add it to itself, its additive inverse has to be itself based on what we talked about last time. And so those points have to have order 2. And those are the only points we were able to come up with that had order 2, and those are all of them. Okay. So we understand the points of order 2 pretty well. So proposition, let's suppose I have an elliptic curve over k. How many points of order n are there? And again, by order n, I mean order n or order dividing n. Okay. It turns out, this is not easy to show actually, but there are at most n squared points of order n in any field extension of k, in any field extension. You can make this extension as big as you want, even all the way up to the algebraic closure of k, and you're still never going to gain more than n squared points of order n on any elliptic curve. Not even just the elliptic curve we're talking about, any elliptic curve. Okay, so that's one thing to be aware of. And so which elliptic curves do we care about, and which fields do we care about? It turns out the next natural thing to do would be to take our elliptic curve, our congruent number elliptic curve, which remember that was given by y squared equals x cubed minus n squared x. And we're going to look at this curve over a finite field fq with q elements, okay, where q is a power of a prime number p, right? So here's the proposition. I actually find this remarkable, but so let's say q is the power of a prime number p. Let's say it's p to the l. And let's say p, of course, is a prime not dividing 2n. We've talked in the past about we don't want our primes p to divide 2n, because otherwise our elliptic curve will actually not be an elliptic curve over this field for smoothness reasons. Okay. And then just So we haven't actually assumed anything. All we're doing is saying, you know, pick a number such that you can make a finite field out of it, and make sure the prime that you're using to generate that number actually gives you an elliptic curve. So the only condition I'm actually going to add here is further assume that Q, this number here, is 3 mod 4. And, you know, Q is either 1 or 3 mod 4. So we're looking at, you know, I don't know, half the time this is going to be true without even doing any work. It turns out then there are always Q plus 1 FQ points on our congruent number elliptic curve. Always. It doesn't matter what Q is. It doesn't even matter what N is, which is what's remarkable. There are always Q plus 1 points whose coordinates live in FQ on our elliptic curve. So really, I want you to note that this quantity here that's telling us the number of FQ points, it's independent of N. N can be anything, and this is still true. And we will use this fact later. Okay. So let's take what we've learned about our specific congruent number curve and see if we can push this any further. So moving forward, let's let Kate.
What happens if Q equals to 1 mod 4 in that case?
The situation is worse. I don't actually know. I don't actually know the answer. I don't. Well, okay, so you're going to see what you need to see from this in just a bit here, actually. Yeah. I'll show you the big picture in a minute. Let's see if we can push this further. So K is going to be a field. E sub n is going to be our elliptic curve up here. Let's call this E sub n. And remember, we actually mean the projectivized version of this. Whenever I write this, I just mean the projective version of it. Okay. And we're going to denote by E sub n of K. That's going to mean the K points on E sub n. So what that means is, think of your elliptic curve as living over FQ. Its coefficients as living over FQ. And then you're only interested, oh, I'm sorry, not FQ, but whatever your field K is. Think of your field as having coefficients in K. And then E sub n K is just the set of all the solutions whose coordinates live in K of your elliptic curve. And then we'll denote by kind of this cardinality symbol. The cardinality of E sub n of K is just, of course, going to be the number of K points on the N. So it's the number of points with coordinates in a certain field that live on your elliptic curve. So I can restate this last proposition with this new language. I can say if Q is 3 mod 4, then, assuming, you know, E sub n is actually an elliptic curve, the number of FQ points on EN is Q plus 1. It's a little bit more elegant way of stating the last proposition. In fact, as you can see, I didn't even bother to rename the proposition. So, by the way, just some terminology in case I happen to actually use it. We won't really use this terminology that much, but I might accidentally slip up and say it. If I give you a prime P, then if I consider E sub n as an elliptic curve over FP by reducing coefficients mod P, then what I end up with is what's called the reduction of En mod P. And we say that an elliptic curve is of good reduction at P if P does not divide 2n. And remember, what that really just means is you get an actual elliptic curve when you do this. You get a nice smooth curve. So really, we're just effectively reducing coefficients mod P. We get a new elliptic curve. This is possible even if your coefficients are rational. And you end up with kind of a new elliptic curve, and you can talk about what are the FP solutions to the reduction of En mod P. By the way, if you've never reduced rational numbers mod P, here's a little exercise for you. What does that actually mean? What does it mean to reduce, like, you know, rational numbers mod 11, for example? So look into that. It's exactly what you think it should be. Okay, now we're going to get onto some big, heavy-hitting theorems today. We're kind of, even though we're not even really close to the halfway point here, we're sort of approaching the halfway point of the argument. And so some big theorems are going to start to come into play here. Let's recall what we know right now. When is a square-free natural number n congruent? The last thing we saw was that it's congruent if and only if this elliptic curve right here has a rational solution, x comma y, such that x is the square of a rational number and has even denominator, and y is just any rational number. So we know this right now. Okay. That's still not that checkable. We have to push that further. The first big theorem that we'll need is Mordell's theorem, which is like a huge theorem in elliptic curves. You know, you've got this group of points, right? What is the structure of this group? Okay, Mordell showed that as long as your elliptic curve is over Q, then the number of Q points on that curve is a finitely generated abelian group. And this is not so obvious. I mean, if you try playing around with this by drawing a bunch of elliptic curves and connecting the dots and adding them like we did above up here, you may even have a hard time convincing yourself that this group should actually be finitely generated. It's not obvious at all. Now, once you know this, once you know that the number of Q points on a Q elliptic curve is a finitely generated abelian group, what tool do you immediately get access to? You get access to the structure theorem for finitely generated abelian groups. And what that tells you is the following. Second, I know this is finitely generated abelian group. I know that it has to break down into its torsion part. So this is the set of all the torsion points, the finite order points. And then direct sum with some number of copies of Z. And because the group is finitely generated, I know this power is finite. This all just follows immediately from the structure theorem of finitely generated abelian groups. So crucial part, R is finite. I really want to highlight this. That's because of the finitely generated up here. So in other words, it's kind of like if you were to very naively look at this group, what you could say is it's like the finite order points and then the infinite order points. But the infinite order points are like finitely generated. Okay, there's only like finitely many copies of Z in this group. Okay, this number R is very special. This number R is called the rank of EQ, or some people just call it the rank of the elliptic curve. Okay. I've heard it both ways. And here comes a crucial proposition. There are only 4 torsion points on our congruent number elliptic curve, regardless of what n is. This is not very easy to prove. Classically, if you want to use a classical techniques to prove it, you actually need Dirichlet's theorem on primes and arithmetic progression, and you end up contradicting that theorem. That's the final step of the proof. It's kind of neat. However, with algebraic geometry, this is easier to prove. Keep in mind when I say things like, "Oh, this is easier to prove with algebraic geometry." Yes, that's true, but algebraic geometry requires, like Akaki brought up last time, it requires much more setup initially, right? So is it actually easier? Yes, if you're comfortable with algebraic geometry, but no, if you're not. This would be the go-to proof in that case. So there's only 4 finite order points on our congruent number elliptic curves, regardless of what n is, if we view them as elliptic curves over Q. Okay, so who cares, right? How is this progressing anything? Here's the proposition. Here's the next step in the congruent number problem. A square-free positive integer n is congruent if and only if this rank is non-zero. So I'll let that settle in for a second. That's a huge statement. And it's actually not that hard to show. I put the proof here, actually. Let's just do each direction. So let's suppose n is congruent. Well, what does that mean? From our previous characterization of congruent numbers, that means there's a rational point on En whose x-coordinate is the square of a rational number and with even denominator. Okay. But the x-coordinates of non-trivial points of order 2 by the above are what? 0, 0, and EI comma 0, where EI are the roots of the right-hand side of your elliptic curve. What are the roots of my right-hand side here? The roots here are easy to see because you can just factor an x out of this. So the roots are 0 and plus or minus n, right? So what is that telling me? That tells me the non-trivial points of order 2 have x coordinates 0 or plus or minus n. But wait a second. The torsion group has 4 points in it. And we only found 3 of them. So there's got to be a rational point of order not 2. And by the previous, I'm sorry, I said that wrong because I forgot to include the trivial point. We found 3 non-trivial points on our curve of order 2. But then there's also the trivial point of order 1 on our curve, right? The point at infinity. So what does that mean? That means we have found 4 torsion points on our elliptic curve. But by the previous proposition, there's only 4 torsion points, right? So that means, wait a minute. So there must be a rational point of order not 2. Why? I think I've confused myself here. There must be a rational point of order not 2. Oh, I see. Because what is our solution that we found? We have this other solution right here. So we have the 4 solutions given by these 3 and the point at infinity, right? So that's 4 torsion points. But there's another solution. It's this point right here. It's the point whose x coordinate is the square of a rational number and that has even denominator. So something over an even number comma y. But look, none of these points satisfy this criteria. None of these points have x coordinates that are the square of a rational number that's got an even and that have an even denominator because n is square free, right? So this point that we found is not one of the 4 points that are in our torsion group. Okay, so by the previous proposition that says there's only 4 torsion points, this rational solution on En has to have infinite order. But the second you find a rational point with infinite order, your rank has to be bigger than 1, right? Your rank has to be positive. So that proves this direction. Now, conversely, let's say I have a point of infinite order. So let's say my rank is positive. So that means I have a point of infinite order. I'll leave it as an easy exercise for you. You can easily show the x coordinate of such a point, of twice that point rather, is the square of a rational with even denominator. Okay, but then what do those points correspond to? They correspond to right triangles with, rational sides and area n under the previous correspondence that we started with today. So this is actually an easy exercise. You can check this. And so we've shown the result. So we have advanced the congruent number problem finally. We have a new set, we have a new criterion for checking whether or not a square-free positive integer n is congruent. And that condition is just look at all the Q points and ask yourself, are there points of infinite order? Let's look at some corollaries here. There's other ways of writing this. The above conditions are equivalent to the following. E sub n has infinitely many rational points. So a square-free positive number in n is congruent if and only if E sub n has infinitely many rational points. Why? Because the second your rank is positive, you're going to get a whole copy of z here. So you're going to end up with infinitely many rational points. You can also see that this is equivalent to the following using this proof above. N is congruent if and only if 2 times E sub nq, so twice the rational points, is a torsion-free abelian group. Okay, and this is equivalent to 2 times e sub n of q minus 0 being empty if and only if r is 0. We're not going to focus on all these. They're just there for your viewing pleasure. This is the one that we're really going to kind of latch onto. This one and the one we started with, because they're sort of the easiest to understand. It's easy for me to explain to people what it means to have infinitely many rational points. It's also pretty easy for me to explain to people what it means to have non-zero rank. These are a little bit more terse, but they do come up in like the proofs of some of the things I'm going to tell you later. So it is good to kind of keep them in the very back of your mind. So let me do this. Let me go ahead and point this arrow to this rational point here. Okay. So in some sense, we should expect, based on our previous correspondence and this equivalence right here, we should expect that the triangles with rational sides and area n should match up with sort of the content of 2 e sub nq minus the point at infinity. And we're not going to actually need this, but let me give you that correspondence. It turns out that correspondence is completely understood. With a decent amount of work, you can show the following. So let n be a square-free natural number. Then the right triangles with rational sides, x less than y less than z and area n, are in bijection with the following. Pairs of points, x comma plus or minus y, that live in this 2 e sub n minus the point at infinity. And in fact, I wrote the correspondence for you here, and you can check that out if you want later when I send these notes out, but I don't really want to talk about it because we don't actually need this correspondence. All we need is this theorem here. This really should just be a theorem, right? This is a little bit more important than a proposition, I think. Okay, so summarize. Let's summarize. A square-free natural number, n, is congruent, meaning it's the area of a right triangle with rational sides, if and only if the number of q points on the congruent number elliptic curve associated to n is infinite. However, remember, what is the congruent number problem asking? It's not asking for, it's not asking for profound equivalent criteria for n to be congruent. It's asking for checkable criteria for n to be congruent. This is not checkable still. It's profound. It's very nice, but it's still not checkable like algorithmically. And so now we want to know, when is this rank? When is the rank of this positive? In other words, when is this group infinite? And for that, we're going to have to delve into some other stuff here. Does anybody have any questions before I go on to the next section? Sunil says the denominator part. Sunil, what did you mean by that?
Sorry, I was just commenting when you thought you were stuck a little bit. I was trying to suggest, but you got it. So
yeah, this is one of those things where you write things down and they're easy, and then you go to give a talk on them 2 months later, and
yeah, I feel you.
Yeah.
Continue.
Yep. Okay, so when is this rank? When do we get infinitely many q points on our curve? Okay, for that, we're going to need to build the so-called L function of an elliptic curve. And that's going to take a little time to do properly, but it'll be worth it. So our handle now is to get, our goal now is to get a handle on the rank of an elliptic curve over Q. When is it positive and when is it 0? This turns out to be a little bit tricky, actually. And remember how I said the very first week that the congruent number theorem, if it were to be used as an algorithm for determining congruence of a natural number, we would actually need a weak version of the BSD conjecture to be true. Well, that's about to come up. The step in the proof where the BSD conjecture appears is coming up pretty soon here. Okay, so imagine I have an elliptic curve over Q. The coefficients are rational numbers. I can take that curve and I can reduce the coefficients mod any prime p that I want. And then what I can do is I can count the number of FQ solutions where Q is some power of P. Okay, this doesn't sound initially useful, but it turns out to be very useful. So in other words, we can take our elliptic curve and count the number of solutions over all finite fields, assuming P is of good reduction, so that we actually get an elliptic curve when we reduce mod P. So is there a way to take all of the FQ solutions to an elliptic curve and combine them into one nice little invariant of the curve? The starting point is to build the so-called zeta function of the elliptic curve over FQ. And here's what it is. It's a function of a variable t. And this E over FQ is just letting you know what elliptic curve over what finite field is this zeta function actually referring to. And here's what it is. You take E to the power of the following infinite sum. You take the cardinality of all the FQ to the R points, and you multiply them by this expression here, T to the R over R. And this sum goes to infinity. That's not a typo. I just never put infinity on the top of my sums. And what do I mean by exponential here? I mean the exponential as a power series, if you really want to know. Okay. Now, what is this doing? This has got information in it about the FQ to the R solutions of my reduction of E, where R is any power of Q that I want. R is running from 1 to infinity. So it is nicely encapsulating all this information that I talked about above, all of the FQ to the R solutions for any R. So you might ask, well, what's the deal with this T to the R and this R and this exponential? Isn't this what we care about? Yes, it is, but this T to the R over R and this exponential allows this function to have very nice properties. For example, you can tackle this series with geometric series properties thanks to this. And thanks to the exponential, taking logarithmic derivatives are very easy, for example, and you get some nice results there. We won't really do any of those computations, but these are not here for no reason. They're not here to complicate your life. They're actually here to make things nicer for you. So theorem, very hard theorem. What do these zeta functions actually look like? For any elliptic curve over FQ, where Q is just any power of any prime, the zeta function of E has the following form. 1 minus 2a sub E, where a sub E is a constant only depending on the elliptic curve and nothing else, times t plus t squared over 1 minus t times 1 minus qt. And this q here is just the q that shows up in your finite field. Okay. This is not easy to show. I have not actually been through the proof of this. I've only been through the proof that this is true in our specific elliptic curves, the congruent number elliptic curves. But showing it in full generality is not so easy as far as I understand. I'll be looking at that stuff later. So let's suppose you know this. Using the nice properties of the zeta function that I mentioned above, the nice geometric series properties and the nice logarithmic derivative properties, it's actually not hard to see that if I know what the number of FQ points are on E, I can actually figure out what the number of FQ to the R points are for any R. And I won't go through the proof of that, but all it really takes is examining one of the reciprocal roots of the numerator here and coming up with kind of a nice expression for this cardinality in terms of this. So really all we need to do is figure out the number of FQ points, and then we'll be able to figure out the rest of these FQ to the R points. So what is this telling us? Based on the very nice form that the zeta function has and this property here, it looks promising that we should be able to package up all the information about all the solutions to all elliptic curves over finite over the rationals, reducing them mod p for any p and looking at any power in some nice way. So that being said, with the newfound hope that we have, maybe we should actually take a look and figure out what is the zeta function for our specific congruent number elliptic curves. And so we're going to do that now. So here's what you do. I'm gonna give you just a few steps in that you would need to go through to proceed. What you do is you take your E sub n. You realize that's an elliptic curve over any field K whose characteristic does not divide 2n. We've known that for a couple weeks now. and you define a new curve out of it. Here's the curve. It's E sub n prime, and its equation is u squared equals v to the fourth plus 4n squared. This n is the same n that's showing up in the subscript of e. What you can do as an exercise, you can show that the points on the affine version of this, meaning don't projectivize it, just view it as an affine equation, are in bijection with the points on the affine version of en. In other words, en minus, oh, I'm sorry. The affine en minus the origin, though. You got to get rid of the origin as well. Okay. And so what you do once you realize that is you define a new quantity. Let's take this quantity up here in the zeta function, and where our elliptic curve is E sub n, and let's give it a name. It's usually called capital N sub r. So capital N sub r is going to be the number of fq to the r solutions on E sub n for a given q. And then we're going to define n prime to be the number of fq solutions on this curve, this new curve, E sub n prime. And as an exercise, it's pretty easy to show. You can show that n1, which is the number of fq solutions on En, is n prime, the number of fq solutions on En prime, plus 2. And if you're wondering where the plus 2 comes from, the origin and the point at infinity are the other two. The origin that we kicked out, and then we also kicked out the point at infinity because we're looking at the affine version of En here. Now look at this. I already told you above, n sub r depends on n sub 1. The number of fq to the r solutions depends on the number of fq solutions. We saw that above. But it looks like n1 depends only on this n prime here. So it seems like once you realize this, that what you should be trying to do is find this n prime. How many fq solutions are there on this curve, on the affine version of this curve? This is not very easy to do. So this takes a lot of work. You need a bunch of number theory. You need to go into Gauss and Jacobi sums and Dirichlet characters and quadratic reciprocity and Legendre symbols and so on and so forth. I'm only going to define those things as we need them. Right now, the only one of those things that we actually need to give the next theorem is I need to tell you what the Legendre symbol is, if you don't know what that is. So what is the Legendre symbol? It's written as like this fraction n over p with parentheses around it. And what does it mean? It's basically measuring whether or not n is a square mod p. So it's going to have value 0 if n is just a multiple of p. That's not interesting. It's going to have value 1 if n is a square mod p. And it's going to have value -1 if n is not a square mod p. So it's just measuring, is n a square or quadratic residue mod p? So in other words, does x squared equal to n? Is there an x such that x squared equals n mod p? That's what this is measuring. Okay. With all that out of the way, all that motivation out of the way, I can now tell you the theorem. We can actually compute specifically the zeta function of our congruent number elliptic curves En. So again, let's take a prime p that doesn't divide 2n. We know by now that that's just to guarantee that En is actually an elliptic curve over fp. Then the zeta function of En is given by the following expression. You can view it as two different ways. You can view it as 1 minus 2at plus pt squared over 1 minus t times 1 minus pt. You shouldn't be surprised to see this, right? That matches exactly what's going on up here. And then here, you can also factor the top if you want. And when you do that, you'll get 1 minus alpha t times 1 minus alpha bar t, where this a here is, of course, just the real part of alpha. That just comes from factorizing the quadratic, okay? Something's wrong here, right? There shouldn't actually be something in front of the t here, right? I don't think so. No, wait, that is right. But then if that's right, is this right? Let me, because there's no coefficient in front of the t squared here. So let me just check if I wrote something down wrong really quickly, so you're not completely, we're not on the same page. I must have written one of the two down wrong. I did. It's the first one. This should have a Q in front of it. So my apologies. Okay. I was going to say that looked a little simple when we were talking about it earlier. Okay, now we already knew this. This is nothing new. This is just the same theorem we already had up here, right? What's new is because I'm talking about a specific elliptic curve here, I can actually tell you like what this alpha is and what this A is and stuff. So if P is 3 mod 4, then it turns out alpha is I radical P. Okay. And then this is kind of answering Akaki's question. You see that the 1 mod 4 case is a little bit more complicated. By the way, this equation for alpha comes from this fact that we covered up here. Where is it? Right here. It comes from this fact that we covered about 3 mod primes that are 3 mod 4. Now, we also know the answer in the 1 mod 4 case. If P is 1 mod 4, then alpha is a Gaussian integer and its norm. So what are Gaussian integers? Gaussian integers just look like A plus BI, where A and B are integers. Okay. Then the norm of alpha is given by A squared plus B squared, where A and B are these numbers here. So if P is 1 mod 4, and we look at alpha as a member of the Gaussian integers, its norm will always be P, okay? And alpha itself will always be congruent to the Legendre symbol N over P mod 2 plus 2I. So it's a considerably uglier situation, but it's known. Okay, we understand what this is. And again, note, look at this. Look at this formula here. Either one of them. Do you see anywhere if P is 3 mod 4 where anything here depends on N? I don't. The only thing here that could possibly depend on N, right, is alpha. But in the 3 mod 4 case, alpha is always I radical P. There's no dependence on N at all. And again, this follows from the previous proposition we talked about in the 3 mod 4 case. Okay, so we have all the zeta functions for all of our congruent number elliptic curves explicitly. We know exactly what they are. Now, what's the next natural thing to do once you have all the zeta functions over all the finite fields? Try to package them up into one big function that takes into account all of the possible primes at once. So all of the FP to the R solutions for any prime P of good reduction. And when we do that, we're going to end up building what's called the L function. I think I'm going to go till 5 today because I started a little bit late. Before we get involved with that, before we try to take all these zeta functions and smash them all together into one big function, we need to be motivated to do this. We need to have faith that when we do this, we're going to end up with a function that has good properties. And what you want to do first is you want to very briefly study the Riemann Zeta function, kind of figure out some of its nice properties. And then if the Riemann Zeta function has nice enough properties, maybe we can build a function out of our zeta functions that also has those same nice properties. Maybe we're motivated to do that. And so let's do a brief overview of the Riemann Zeta function. We're going to need to know about it anyway, whether or not we use it as a toy case. First of all, what is the Riemann Zeta function? It's the following infinite sum. So S here is a complex variable. And the Riemann Zeta function is the following function. You take the sum from 1 to infinity, specifically n equals 1 to infinity of n to the negative s. Okay. And you restrict the real part of s to be bigger than 1 so that this makes perfect sense in the complex plane. As an exercise, this is very easy to show. You can show there's another expression for the Riemann Zeta function, and here it is. It is given by the infinite product over all possible primes P of 1 over 1 minus p to the negative s. I know that looks a lot different than this, but it's not hard to show in the slightest. So what does this mean? This means already, if we go back to our zeta functions for our elliptic curve, maybe, like look at this expression here, 1 over 1 minus p to the negative s, and then go up here to our zeta function. Look at our denominators. What would happen if we, substituted in for t, maybe p to the negative s? Wouldn't we also have expressions that look like 1 minus p to the negative s in our denominator? Yes, we would. So we're already motivated to do that when we go to smash all of our zeta functions together. Maybe we'll take a product over all these, over all primes p, and maybe we'll just replace t with p to the negative s. I don't know. It turns out that's not quite all you want to do, but that's mostly what we're going to end up doing. Okay. If you've never heard of it, what's the gamma function? Capital gamma of s. S is again a complex variable here. It's the integral from 0 to infinity, e to the negative t times t to the s minus 1 dt. And I'm sure most, if not all of you know that this function is famous for interpolating the factorial function in the sense that if you plug n in for s here, you actually just get n minus 1 factorial. And this function is defined on the right half plane. Okay. What is the big theorem about the Riemann zeta function that we are going to be relying on? It is the analytic continuation of the Riemann zeta function. Here's what the theorem says. The Riemann zeta function extends analytically to all of the whole complex plane. Remember, it's only initially defined to the right half plane, to the right of 1. But you can extend it to an analytic function to all of the complex numbers, except you are going to pick up a simple pole at s equals 1 with residue 1. Okay, no one cares. Okay. In addition, you get more than this. You get more than analytic continuation. You also get the following. Let's let lambda of s be the following expression. Pi to the negative s over 2 times the gamma function evaluated at s over 2 times the Riemann zeta function evaluated at s. Then it turns out this gadget here satisfies what we call a functional equation. In other words, lambda of s is always lambda of 1 minus s for all s. Okay, so what does that tell you? One way of wording that is the Riemann zeta function has we call this a functional equation. Its critical value is 1/2, because what happens if you plug 1/2 into both sides? You get a fixed point on each side. And the critical strip of this functional equation is from 0 to 1, where the real part of s is between. So it's this vertical strip where the real part of s is between 0 and 1. What's the motivation there? These are the smallest and largest values that make this functional equation interesting, basically, that give you this kind of invariance. Like if I were to plug something bigger than 1 into this, then suddenly I'm ending up with like negative numbers over here. And if I were to plug in something smaller than 0 over here, I would end up with negative numbers over here. So I'm kind of losing the elegance of this functional equation here. The elegance is really happening on this vertical strip in the complex plane, okay, between 0 and 1. And we're centered at 1/2, so we call that the critical value. These properties of the Riemann zeta function give us hope. Analytic continuation to C, and a nice solid functional equation on a nice critical strip with a critical value. Those properties are going to be key moving forward for us. We are motivated now to try to take all of our zeta functions for our elliptic curve, smash them together, and hopefully we end up with a function like the Riemann zeta function that's got similar properties, maybe an analytic continuation, maybe a nice functional equation, something like this. And so I'll end today by defining for you the L function of our elliptic curves. Here's what we're going to do. We're going to do exactly what I said. We're going to take E sub n and all of its zeta functions. We're going to smash them all together and hope for the best. In doing so, we produce what's called the L function of the elliptic curve. And here's what it is. The L function of E sub n is a function of a complex variable S. And what we're going to do is we're going to product over all primes P of good reduction our zeta functions, but not really just our zeta functions. We're going to make the motivated substitution that we talked about earlier. We're going to replace T by P to the negative S so that we get this nice Euler product to pop up. So you can see here, I don't have capital T anymore. I've replaced T by P to the negative S, just like I said I was going to do earlier. And then we're going to stick that in the denominator so that we hopefully end up with something like convergent here. And we're going to do zeta of S times zeta of S minus 1 divided by this product we made. So it's exactly what we wanted to do, but we end up with this extra little numerator here. Why do we add this extra little numerator in here? Because if you write down the Euler products for these two guys, you see that they cancel the really stupid terms in this product, basically. And what you end up with as an exercise is you end up with an explicit formula for very nice formula for your L function. And here's what it is. It's the product over all primes P of good reduction, meaning primes not dividing 2n, of 1 over 1 minus 2a sub n, P to the negative S plus P to the 1 minus 2s. And what is this a sub np? It's the a sub np from up here, from our zeta functions. There's one value per n and per p, right? So I should have probably just written this a sub np to begin with. And you get this nice formula because these zeta functions up here cancel some stupid stuff that you end up with in the denominator that you don't actually care about. Okay. And so there's your L function. And so starting next time, we're going to be talking a lot about the L function. And we're going to try to progress the congruent number problem even further. What do we know right now? Just to recall, square-free natural number n is congruent if and only if the rank of the group of Q points on the congruent number elliptic curve E sub n is positive. And that's the same thing as asking that there be infinitely many rational solutions to the congruent number elliptic curve. Okay. So I'll stop there and I'll take questions. If you want to ask questions, type them in chat, unmute yourself, do whatever you want. And whatever you got, I'll answer. Or if you have any comments you want to make, that's fine too. Either way. Give it about 30 or 60 seconds or so. Thanks, Jim. Appreciate it. Hope to see you next week. All right, everyone. I think that's thanks, Jingu. Appreciate it. Hope to see you next week as well.
I thought Akaki would at least have a joke.
I bet you Akaki bounced out when I took till 5 o'clock to stop. I've been stopping at 4:50 recently, but I decided to go a little longer today. Yeah, there should be some joke, but I mean, sorry about the beginning. I had, you know what, Jim? I didn't even know. I am not very good at looking at the participants list, even though it's pulled up right in front of me. I never check it, so that's perfectly okay.
I was watching it.
Okay, as long as somebody's watching it, then. All right, everyone. I'll see you next week for some more L function action.
Okay. Bye.